All right, good afternoon, everyone. So last time we learned about two ideas. We learned about ensemble methods, where we take simple classifiers or regressors and we somehow train them to act differently than each other, and then we combine them to make a much stronger classifier or regressor. We also learned about decision trees, which are a way to build classifiers or regressors that's different from what we've considered so far. And then at the very end, we combine them together, and we have this idea of a random forest where you have a number of simple decision trees that on their own don't do all that well, but then you train them so that they're diverse, and you essentially combine them or ensemble them to finally get a really good method. So that's the random forest method. And what makes this method kind of distinct is the way that you are doing things in parallel. So you basically train each of these trees in parallel, and then once they're trained, you just sort of average them to get the final forest. So what we're going to talk about today is a different approach that, instead of being parallel, is sequential. So the idea is that you start with a data set, you train a model here, looks like a tree, and then you look to see where, how that model did in terms of which samples were errors and which were not. And then you train another tree that basically you do something like weighting the samples that were in error here. You weight them stronger when you design this tree so that this one is going to do better than the first one, at least on those samples. Maybe it does worse on some other ones. And you keep doing this. And so you train sequentially these different models. And then finally, you do combine them together to get a method that is, a boosted method that's going to be better than each of the individual trees. So again, these methods tend to be tree-based. They don't necessarily have to be, but they tend to be because trees are pretty friendly to design. And the main thing is that these are trained sequentially. And this is called boosting. And so finally, what we'll do today is we'll talk about three strategies. A simple one that's kind of an easy introduction, and then we'll talk about an improvement that's a little bit more complicated, and then we'll briefly talk about a method that is still one of the state-of-the-art methods today called XGBoost. Okay, so we're going to start with the simplest one, which is AdaBoost, and this will set up some of our notation and some of the basic concepts. So for AdaBoost, our objective is to train an ensemble of predictors. These predictors are going to be called FM. Little m is going to go from 1 to big M. And these predictors here are like these guys. We want to train those things. And we're going to use a for loop. And so first, for a given value of m, we're going to train this predictor FM to minimize some weighted loss. So this part is something that we're familiar with. It's a loss between the ith training label, and this is our prediction of that label from the ith training feature. So we can sort of think about this as like a yi hat that we're making with the mth predictor. So that part on its own should be familiar, but then you can see, and then this part is familiar, we of course want to sum over our training samples, but this is what's kind of new, is that we're going to be using a different weight on these losses, and the weight is going to depend on the stage within our sequence, as well as on the sample index I. And the idea here is we want to assign larger weights to samples that have higher loss or that seem to be in error. Once we're done designing these sequentially, F1, F2, and so on, we will finally come up with this boosted version, which has a capital F here. And that's going to be, you can see it's a weighted weighted sum, and then we also want to learn these weights. So in the end, we want to learn a sequence of predictors as well as a sequence of weights. So we can do this with regression or classification, but to keep things simple, we're going to focus on binary classifiers today. And notice that these are hard output classifiers. So rather than outputting a score or probability, these are outputting either 1 or -1, and that's it. Okay, so again, you can develop AdaBoost for regression, for non-binary classification, but we just want sort of the main idea to use as a building block. Okay, so this is the derivation. Just got to go through step by step. So again, we're working on binary classification. We have training data, as always, pairs of x, y's, and in this case, our y is going to be ±1. And we are designing these base classifiers, these FMs, and as we said, these FMs can only output ±1, hard outputs, and we have capital M of them to design, and we're going to design them sequentially. So when we're at step little m in the sequence, we want to design this boosted classifier, which, as you can see, will take the previous boosted classifier and just add one more term, which is our scaled, alpha M scaled version of FM. And you can see that when you do this sequentially, you eventually build up this once you get to the capital M stage. Okay, so you're just adding these terms on one at a time like this. Okay, is it making sense so far? Okay, so this is how we do it. We initialize F0 at 0, so that's just like the 0th stage is basically nothing. And then we say design stage 1, stage 2, stage 3. So at the mth stage, we want to design a scalar weight, alpha m, which we're going to say is positive, and we're going to design our base classifier fm. And our objective, to keep things simple, is we're going to minimize the exponential loss. So this is not a loss we've seen before, but it's not so different from things we've seen, and it makes a lot of sense when you think about it. So remember, so these little FMs are ±1, but because of these scalar values, the capital F's are not going to be binary ±1. They can output some real number. But as you could expect, we want their outputs to agree with the true yi's. So when you look at this sign corrected thing, yi times fm is going to be greater than 0 when you make a correct decision, right? When xi comes from a positive label and you multiply it, the label 1, you multiply it by 1, that thing's positive. Or when xi comes from the label -1, and then you multiply, that should be negative, and you multiply by -1, and the result, again, is positive. Okay, so when this is correct, this is positive, which means you're exponentiating a negative number, which means you get a value less than 1. On the other hand, if you make a mistake, then this term is negative. You hit it with the minus sign, it becomes positive, and now you're going to assign a weight greater than 1, right? So this is doing the right thing. It's assigning smaller weights when we're correct and larger weights when we're incorrect. So that's what this exponential loss is doing. And as we've seen many times, working with exponents, a simple loss like this, it's very easy to do derivations. It's very nice for that. Okay, so this is our goal then. We want to go through m equals 1, m equals 2, and so on. At each point, we want to design alpha and fm to minimize this exponential loss. Okay, and this is tractable, as we'll see. So when we think about, let's see, this script, let's see, did I? Oh, okay, here we go. Yeah, so this script LM, this is the exponential loss at stage little m. So here's what we have. And all I did here is I plugged in, for this capital FM, I plugged in this value here, and then we get this expression. The next stage is we can see that we have an exponent of a sum of things, which means we can break this into two exponents, one e, another e. And when you look at the first one, it does not involve alpha m or fm, which are the things we're designing. So we can think of this as a constant for our design, and we're just going to give it a name, WMI. This is the thing that involves the design variables alpha m and fm. Okay, so the next thing we do is we're going to split our sum into two parts. One is a sum over the samples I, for which we are making correct decisions. Remember that fm can only be plus minus 1, yi can only be plus minus 1, so when we're correct, they agree. When we're incorrect, they disagree. So we're breaking the sum into correct and incorrect parts. And then one other little thing we're going to do is we are going to complete this sum. So this is the one that, where it's missing the incorrect parts. So we're going to add the incorrect parts back in, but we're going to compensate by subtracting the incorrect parts here. Okay, so this plus this equals this. Okay, and the reason we're doing this is we have now separated the alphas, which appear here, from the classifier f, which appears here. And so this is going to be useful for design. Actually, we have an alpha over here too, but the key point is that our f's are only in this term. So we can focus on, when we design f, we can focus on this term alone. Okay, is everybody okay so far? All right, so again, we want to minimize this term. We know we want to minimize it because this is guaranteed to be positive, so we want to minimize that. And this has a nice interpretation. So this is summing over the places where we made a mistake, and for each of those places we have a weight. So you can think of this, if these were all ones, this would just count the number of errors we made. But because these are not necessarily ones, this is we can call it a weighted misclassification loss. So here again is another way to write it. This indicator function comes alive when we make a mistake, and those are the terms that add to the sum. And if we did not make a mistake, then for those i's, they contribute nothing, and so that's like here, they're contributing nothing as well. Okay, so basically, this shows how we design our classifier. So at step m, what we do is we initialize all the weights to be equal to 1, and then we just train f to minimize our misclassification loss, which is a pretty standard thing you can do. It's easy to do this with a tree. Then, that's the first step. At later steps, we will be able to compute these weights, and we'll see that the weights are large if our previous boosted classifier made a wrong decision. And so by putting those weights in here, we're saying, this time around, don't make a mistake on that sample because those are the samples we were wrong about with our last boosted classifier. So as this gets, as the stages go on, you can figure out exactly which samples you should focus more attention on. And so that's essentially what's happening here. Okay, so is that part kind of clear? All right, so we figured out how to design or how to train the Fs. Now the last thing we'd figure out is how do we train the alphas. So we want to minimize this loss, and we know our F, so everything is known except for these alpha terms. And we can just use the standard approach where we take the gradient of this with respect to alpha and set it to 0. And when you do that, you find that the optimal alpha takes this form, where epsilon, you can interpret this as a weighted error rate. So if these w's were 1, this would be basically you're counting on in the numerator the number of places you made a mistake, denominator the total number of samples. But here we're using weights, so instead of just a regular error rate, it's a weighted error rate. Okay, so that's basically how you can set alpha. And so now we figured out all the little steps. So just to summarize, in the first iteration where little m equals 1, we set our weights to 1, and then we compute FM. We train FM this way. Then given our FMs, or given our F1 and our weights, which we know, we initialize them, we can compute these error rates. From the error rates, we can compute alpha. From alpha, we can compute the first one of these, which would be 0 plus alpha times f. And now we have the first f, big F. And given the first big F, we can compute our weights. So our weights are given over here. So we can do that for m equals 1. And then once we have that, now we know the weights for m equals 2. And we go through this procedure again. And we repeat this procedure all the way until we get however many stages we want. When we're done, we have this m-stage boosted classifier. And if you are given a test sample X, you just put it through that boosted classifier and predict a label, and that's how we use it. Okay, so this is known as AdaBoost. Here is here's sort of a just illustrative example of how this works. So here we have two-dimensional features at iteration 1, and we're gonna use a decision stump. So a stump is a tree with one level. Super simple. So basically, it's all you're doing is you're partitioning the space of x1, x2 into 2. You either put a line horizontally or a line vertically. That's what stumps do. So in this first iteration, you can see we have these positive samples, we have these negative samples, and we decide to put our decision region here. And so what that means is these guys are going to be correctly classified. These ones are going to be incorrectly classified by that first stage. So at the second stage, you can see by the size of the pluses, because we made errors on them in the previous stage, we are weighting them more. So now with this next iteration, next classifier, we want to make sure that we don't get these ones wrong. So this time we're going to choose a threshold over here. So all these blue pluses will be correctly classified. These will be correctly classified, but these guys will be incorrectly classified. And so the next time, we want to make sure that we don't classify those wrong. So we make those, this is showing that we use a large weight on those. And this time, we're going to choose a threshold this way, and so on. And then you can also see that along the way, we can compute our alphas, which happen to take these values. And finally, this is our boosted classifier. This is going to return not necessarily a plus minus 1, so we need to take the sign of it to get a hard classification. But when we've done that, you can see the final classifier is a weighted sum of these three, which is going to give us this shape. And as you can see, this is going to perfectly classify our training data. We can do that with 3 of these. We don't really need any more. Okay, so just an example of how you can use AdaBoost with decision stumps to take these 3 really primitive classifiers and put them together to get a classifier that perfectly classifies your training data. Okay, so in sklearn, you have this AdaBoost classifier. By default, it uses 50 decision tree classifiers with depth 1. These are these stumps. And there's also an sklearn AdaBoost regressor, which uses 50 decision tree regressors of depth 3 by default. But of course, you can change those if you like. Or you can use more decision trees or less. Okay, so this is sort of just an introduction to how we can do sequential learning of these classifiers and put them together to get a much better classifier. Any questions on anything here with the derivation or the concepts? Okay, so this is our building block. This is the simplest case. So now we want to try to be a bit more general. And this is where we get something called gradient boosting. So now our goal is going to be to design this boosted predictor, again, using the same notation, capital FM. M is the number of stages. And we want to minimize a training loss of this form. So as you can see, it's just a sum over the training samples. We have some loss L, which we can choose. You know, maybe we can choose one for regression, a different one for classification. And here we just have our boosted classifier applied to our training data, and we just want that this is minimized. So it's kind of the most generic thing you can imagine. So now the way we're going to get our boosted classifier is exactly the same as before. It's the sum of the base classifiers, the little fm's, scaled by an alpha m. And we are going to assume, this is very important, that our base classifiers have a particular form. So for example, maybe our base classifiers put out binary decisions, and that's just a constraint we have, or maybe they put out real numbers or whatever, but they have a particular form. And we can think about an example of this that we just saw is AdaBoost. So AdaBoost is a particular example of this, where we used a very particular loss, which was this exponential loss, and we used a particular kind of predictors here, which were binary plus minus one predictors. Okay. So what we'd like to do now is repeat that. We'd like to do this, if possible, for general losses L and general classifier, base classifier structures FM. Okay, so that's the goal. And so ideally, this is what we'd like to do. So we're going to first train our first base classifier to minimize the loss as usual, and then we'll initialize our first boosted classifier with the base classifier. And then for the remaining base classifiers, we're just going to add on to our last boosted classifier this thing, which is going to be our alpha m FM. And this is, again, the same thing we did last time. We're just building up this boosted thing by adding one term at a time. But as you can see here, we want to choose the alpha m and the FM jointly that minimize the loss of this new guy. So this FM is essentially what we want to perform well. Because when we take our last boosted classifier and we add on this new thing, that would be the model at the end of the stage, and we want to figure out are the additions that make that model minimize our loss. That would be great if we could do that. Turns out that is just too difficult. We can't attack that totally general problem. So instead of doing a strict optimization here, the idea behind gradient boosting is we approximate that with a gradient step. Okay, rather than exact alpha m times fm, we take our last boosted classifier, and you can see we take minus gradient of the loss with respect to the boosted classifier, and we're going to use alpha m as a step size. So that's the main idea behind gradient boosting, or one of the main ideas. But we have another problem to deal with. Remember that we need our base classifiers to be, or base predictors to be of a particular type. Maybe they're like decision stumps or something like that. And when you look at what's happening with, this form of update, you can see that this is not so this is sort of the form we want. This is the form, what we're doing. You can see that this will have the structure we want, but this will not necessarily have the structure we want, because we can't guarantee that the gradient here gives us something that is in this set of classifiers. So that's the problem. We're limited to updates of this form, where F is a set of base predictors, But gradient descent gives us gradient descent gives us something like this, and you can see that it just won't have the right form. So instead of accepting this gradient version of FM, we are actually going to train FM of the form we want. For example, maybe this is like decision stump, to be close to the gradient. So that's the final full idea. Okay, so now we can understand exactly what we're going to do. And just notation-wise, we're going to look at this gradient and realize that this is going to be a sum over our training samples of a gradient where we just look at the ith training sample. We're going to give that the name minus RMI. So I refers to the training sample, M refers to the stage of boosting we're at. And when you look at it this way, we essentially want that, so the negative sign in this R is kind of compensating for the negative sign there. We want that this FM is close to, if I apply this FM to xi, it is close to this. Okay, so we train F to minimize this loss. So it looks kind of like a regression loss, right? We have a square, sum of squares. The targets in this case are actually these gradients, and this is our predictor. Our predictor might, if we're doing classification, might report plus minus 1, or regression, it might report a real number. We can handle any of those options in this framework. But let's say that we have a way to train F to minimize this. Once we're done with that, the last stage is to choose alpha M. So we can come back to this idea where back here we said, choose alpha M to optimize the loss. We can do that still. So here we're going to add our FM that we just decided to our previous boosted classifier with some scaling alpha, and we will just do a search, maybe like a grid search over different alphas, so that our loss over all our training samples is minimized. So now that we know our FM and we know our alpha M, we just multiply them together to add this new term to the previous boosted classifier to get the next boosted classifier, or predictor, regressor, whichever one. Okay, so that's the idea behind gradient boosting. Sounds a little bit convoluted, but it was a big advance, and it's quite general. You can use it in a lot of applications, a lot of formulations. So let's see, are there any questions on this? I realize there's a lot of details here. Might be the sort of thing where you need to take a look at it again on your own time. But are there any questions that I can answer right now? Okay. So one thing is that in practice, this choice of alpha, this optimized choice of alpha, is a bit aggressive, and it usually works better to put a little factor less than 1 in there, mu, to be a little less aggressive with the update. And so when you look at what's done in sklearn, you have the gradient boosting classifier, you have the gradient boosting regressor, and by default, the classifier uses 100 decision tree classifiers of depth 3, and by default, a mu of 0.1. And then the regressor is very similar, it uses 100 decision tree regressors of depth 3 and a mu of 0.1. Okay, so here's just a simple example where this gradient boosting regressor was trained, and then what you can do is you can pull out of it the different stages. And in this picture, the different stages are plotted. So the first stage, okay, so this is a regression problem. We're trying to predict this curve, this smooth blue curve, from the dot samples. So that's our goal. And when we look at the very first predictor we're using, I think it's just using, it's a very simple regression function. It basically is just this line. So, anytime the input is less than that number, it reports this output, and anytime it's greater, it reports that output. So that's what we have at the first stage. Then it's also plotting third stage, which is this green function here, which, as you can see, is a bit more sophisticated. It looks more like that blue curve, but still not much. And you can keep going, and it looks like here they used 2,000. They had 2,000 stages, and the red curves show as you get more and more stages, you eventually get to this function, this kind of stair-steppy function, but it looks, much closer to the blue line. And in some sense, you can think of the number of stages that you use as doing some sort of bias variance trade-off. When you use a few stages, you get some pretty primitive curves that have a lot of bias, but they're not too sensitive to your data samples. As you go through many stages, you get curves that are highly sensitive to your training samples, which means they have a lot of variance, but very little bias. So you can use the number of stages to trade off between the bias and the variance. Okay, so that's gradient boosting. Nice technique. What people use in practice nowadays is something called extreme gradient boosting, which is just an evolution or improvement of gradient boosting. This thing is famous for winning many machine learning contests. These are like for low dimensional data. I'm not talking about images and so on, but if you have something with dozens of features, maybe hundreds of features, XGBoost is sort of like one of the first things people will try. You'll find it's much easier to design a model with XGBoost. It has really good defaults. You just run it, and it usually gives a really good solution. You can definitely tweak a lot of things and make it a little bit better, but out of the box, it gives a really good prediction. And the main things that it uses beyond gradient boosting, instead of a gradient, it uses a second-order Taylor series approximation. So instead of just looking at slope, it looks at slope and curvature. It uses a regularization that helps to guide the depth of the tree. It uses sophisticated tree search, and then it uses a lot of parallelization and hardware acceleration tricks. So we're not going to talk about the last two, but we'll talk now a little bit about the first two. And although the XGBoost package is not part of sklearn, it's just a separate thing that you can import, and then once you do import it, it works. It's written to work exactly like sklearn. So all the typical ways that you use sklearn, it's fully compatible and it works the same way. I'll show you an example. Okay, so this is the derivation. Similar to what we saw with gradient boosting, we're designing our boosted predictor like this. This is actually simpler in the sense that we have no alpha m's, no scaling terms. We just have a sum. The boosted predictor is just a sum of base predictors. Okay, and so what we would ideally like to do, like with gradient boosting, is we first design our first base predictor to minimize the loss summed across the training samples. Here you can see we're going to be using sum loss function. Try to be as general as possible. Once you have that first base predictor, you set that as your first boosted predictor, and then you design the next base predictor. And ideally, this is what we'd like to do. We'd like to optimize the base predictor so that when we add it to our previous boosted predictor, that this, and we're going to minimize now the training loss, but also a regularization term. Okay, so this is a new addition, but it's regularization like always. This new regularized cost, we're going to minimize that, and once we do that, we have our new base predictor. We add it to the previous boosted predictor, get our new boosted predictor, move on to the next M, and so on and so on. So we design them one at a time. Now it turns out that, not surprisingly, this very general optimization problem where we're using a generic loss, generic F and everything is too difficult. So we're going to approximate it not with a gradient, but with a second-order Taylor series approximation. So it goes like this. So here is the loss that we are focusing on here. You can see this is our previous boosted predictor plus our new base predictor. We're going to take a Taylor series of this using the second argument, and we're going to take the series about this reference point. So this will be the constant term in the Taylor series. Then this is the linear term. We're going to have something times f, and then we're going to have another something times f squared. So the linear term in the Taylor series, the quadratic term, and like always, the linear term in the Taylor series is just the gradient of the loss evaluated at that reference gradient with respect to f. And then the second term here is just the second derivative, the curvature basically, second derivative of L with respect to f. Okay, so that's basically the approach. And now you can see that when we are designing FM, here, this is not a function of the little FM. So we don't really have to worry about putting that back into our cost. We can just focus on these last two terms. They're the ones that depend on FM. So this is what our loss becomes, and we have our regularization as before. Okay, so the question is, how do we proceed with this? So we're going to now focus specifically on decision trees as our predictor, and we're going to say that the max number of leaves in our decision tree, we're going to give that the name L. This is just the notation. Also, importantly, remember that we can think about a decision tree in basically two stages. What a decision tree does is it takes an X, our input, and it figures out which leaf that X maps to. And once we know which leaf it maps to, it just looks up in a table the output Z to report. So let me just go back to page 10. So again, we get a new sample X, or maybe even this page. We get a new sample X. We figure out which region it falls in. Let's say it falls in this region, and then we just look up for that region what is the value Z of the region. Right? That's how these decision trees work. So you can think of this function over here, QX. We'll call QX the decision tree, the part of the decision tree that tells you which leaf it falls in. So it's going to report a number between 1 and capital L, where L is the maximum number of leaves. So in this case, a number between 1 and 5. Once you know that, we will just look up in a table. We have an output for each of these, like Z1, or actually Z1, Z2, Z3, Z4, Z5. Okay, so that's how we're thinking about things. Let's go back to the page we were on. Okay. So we are going to, just in terms of notation, we are going to call Q as the part of the decision tree that assigns the input to a leaf, L, and then we're going to call ZL the predictor output that the decision tree uses for leaf L. Okay, so when you put those together, you can see that the decision tree as a whole, Fx, is really Z sub Qx. Does that idea make sense? Figure out the leaf, look up in a table. Okay, so this is the regularization that XGBoost uses. It has two terms. The first one is just a sum over all the leaves or all the regions of the squared output value, ZL squared. This is going to be some, lambda is some tuning parameter, some weight that we can choose. So that's the first part of the regularization. The second part of the regularization you can see is how many leaves there are in the tree. And then it has a parameter gamma that's also a tuning parameter. So this is the regularization we are going to use over here or over here when we optimize or when we define this regularized cost. Okay, so we can finally see what does it take to do this minimization. So the first thing we're going to do is rather than writing the sum over the sample indices I, we're going to break it into two sums. We're going to write it in terms of a sum over the different leaves, and then a second sum which looks at all the samples that correspond to leaf L. Okay, so here, raw samples, here it's leaves, and then which samples per leaf for that leaf. The other thing we're going to do is just to make the notation easier, we're going to omit the M notation. M, if you remember, that's just the stage of the boost we're at, so that's not really helpful now. We're going to take away all the M's up here just to try to lay bare what's important. Okay, so over here we're going to have GI, as you can see. Over here, we can just call this ZL, because we know that for all the xi that map to the lth leaf, this is just going to be ZL. So we have a ZL there. Over here, this is just HI, because we dropped the M. And again, this is ZL squared. And then our regularization, which we said is this, we're just rewriting that down here. Okay, so now that we've written it this way, you can see that we are trying to optimize both over the values of the leaves in the vector Z, all the ZLs, as well as the tree function itself, Q. So let's first notice that we have a quadratic in the Z's. So we have a squared terms, linear term, constant term. So here we're just writing this linear quadratic constant. So we're just, organizing it into a quadratic. And you can see that the linear term is this sum over I times the GIs. The quadratic term is the lambda from here, or 1/2 times that lambda plus the sum over the HIs. And then our constant term is over here. The L got absorbed into this sum. Okay, so we have two things to design. The scores Z, or the output Z, as well as the tree itself. Okay, so what we can do first is let's design the scores. So to do that, all we have to do is take set the gradient of this with respect to Z to 0. Because it's quadratic, that's very easy to do. You find that ZL is this ratio of stuff. You plug that back in to your cost, and now this is the remaining optimization problem. Here is our tree we have to design, and here is basically the metric that we want to use to design our tree. So when we first talked about designing trees, we talked about inhomogeneity, like Gini metric, variance, all these different things. So what we're saying now is, forget those ideas. We have a very specific metric that we want to use for XGBoost to replace those inhomogeneity things, and it's this exactly. And so that's really the main idea. The tree can be designed just as we did before, where at every stage of designing the tree, you choose a single feature J, you search over a threshold that maximally reduces loss after the split. And now the loss that we're working with is this. So, we look at all the different features, all thresholds, we choose one of them, and that's going to split our data set into two. It's going to take all our training samples and split them into these two sets, which is like a branching of the tree. And then you take your S1 and you try to split that again into two. You take your S2, you try to split that, and so on and so on. So the one question is, when do you stop? So to understand that, you can look at how much, if this is the total loss, how has the loss reduced after each split? Has it in fact gotten smaller? If so, good. But if you find that the loss actually got bigger, that's a sign that's saying, no, you went too far, go back. You actually had a better loss before. So this is how you can see what the loss reduction will be. So this is the loss before we do the split. And the main thing to notice is that when we take these sums, we're taking a sum over all the samples I in this set. So this is the loss before the split. This is the loss after the split. And now you can see in the second one, we basically have, it's like we have a version of this where for the samples I, we only are using the ones in S1. And then we have another version over here where we are using the ones in S2. Okay, so this is the loss before the split. The sum of these two things is the loss after the split. And so the difference between them is how much the loss has reduced. So again, if it reduces by a positive number, that's great. We made progress. Move on to do another split, either split S1 or S2. But if you find that the best you can do is a negative number, you know you don't want to split, it's time to be done with that branch. Maybe move on to a different branch. Okay, so that's basically the ideas behind XGBoost, and there's definitely more to it. There's a lot of interesting architectural stuff, and it's pretty complicated though. You can check out the details in the original paper, but these are sort of the main details that I wanted to explain to you. So here is basically just the last slide in this unit, which is some code of how to use XGBoost that I got off this website. So as you can see, we just need to import XGBoost, or the XGBoost classifier. And we load a data set. We split the data set into features and labels. We do a test train split. And here you can see model equals XGBoost classifier, exactly what you would do for sklearn, model.fit on your training samples, model.predict on your test samples. And then here you can actually do the predictions to see if, basically you're just rounding the values output by the model and then predicting the accuracy. So it's very easy to use. It's very much like sklearn. And it's, an important part of your project. If you guys are looking at the tree methods, you probably want to focus on random forests and XGBoost. In both cases, there are a lot of little parameters that you can play with. There's some nice tutorials out there that give recommendations on which of those parameters will give you the most bang for your buck in terms of trying to tune them. You'll find that it works pretty well just with the default parameters, but you can get it to work a little bit better. And again, you'll be competing against your classmates who are trying to do the same thing. So even though it works pretty well, you're trying to do better than the average, right? So so that's really all I had to say for this unit. So we talked about ensembling simpler predictors to get better ones. We talked about designing them in parallel. We talked about designing them in series. And these are just a really nice set of methods to know about and to use for practical machine learning. So just some high-level announcements. So Unit 9 on CNNs, deep networks, is going to be the last homework and lab for the course. So there's not going to be any homework or lab for this unit or any future ones so that you have time to work on your projects. Okay. There will be quizzes for this unit and for the next two, but just quizzes. So that's probably good news, right? Yeah, so because the final project is a important part of your grade, so you've got to have some time to work on it. So that's that. Take a close look at the dates for the quizzes because of Thanksgiving, the holiday, and because it's not going to be like a quiz due every Friday. So just take a look. We basically have 3 quizzes left. One of them is going to come alive for this unit. Will come alive at 6 p.m. today. I think it's due the Monday after Thanksgiving weekend. And then the next 2 units, so on Friday of this week, I'll go over the midterm with you. And then next week, either next week or maybe I'm not sure if I'll skip that week. But we only have 2 units left to cover. Is that right? Yes. We have 11 and 12. So unit 11 is going to be on PCA and related ideas, non-negative matrix factorization. And then unit 12 is going to be on clustering. And these 2 remaining units are, up till now in the course, we've done supervised machine learning where you always have like features and then labels you're trying to predict. When we move to these next 2 units, there's not going to be any labels at all, just features. So you're just trying to understand the features themselves, understand their structure, see if you can cluster or group similar feature vectors together. So it's going to be kind of the spirit is different, but it's very important and useful stuff. So that's what we're going to be talking about in the last 2 units. So, all right, any other questions on anything at all? All right, so we're in the home stretch. So see you guys on Friday.